The objectives for my talk today are to provide some emerging information about understanding of the genetic diversity of mature T-cell malignancies, gain information about how genetic alterations in these tumors may aid in the diagnosis, and then importantly, how our understanding of the genetic basis of these relatively rare tumors provide opportunities for tailored therapies for patients currently and in the future. So the way I organize my talk, I'm going to give a very brief background about T-cell malignancies, and then talk about 5 different areas that we have learned quite a lot about. And this is mutations that occur in a group of T-cell lymphomas that arise from the follicular T-cell origin. Talk about the T-cell receptor-associated mutations that seem to be common in many forms of T-cell malignancies, epigenetic modifiers and the mutations that seem to be quite prevalent in a variety of T-cell malignancies, and then the phenomenon of alterations and activations of components of the JAK STAT pathway that occur in many forms of T-cell lymphomas. And then rearrangements that seem to be highlighted in the ALK-negative anaplastic large cell lymphomas. And then talk about how the implications of some of these data may have for diagnosis and therapy. So the WHO classification, very simply, mature T-cell malignancies are going to be the topic of discussion today. I'm not going to talk about any of the others. And interestingly, I think in contrast to the Western Hemisphere and European countries where T-cell lymphomas are relatively rare, we understand that in Asian countries and countries of Latin America, including Peru, the incidence of T-cell malignancies is much higher, maybe higher than I listed here. And so with the focus of studying lymphomas that are not as commonly studied, as Koja have outlined in his research-focused talk, our lab has spent quite a bit of time learning about some of the genetic alterations in T-cell malignancies. So this is the 2017 WHO classification. There are over 28 different subtypes of T-cell lymphomas. The ones that are asterisked, or highlighted by the asterisk, are the ones that are provisional entities or newly accepted entities in the WHO 2017. And while we are learning more about the conceptual and genetic bases that may group these together, clearly we understand that these are very heterogeneous diseases at the clinical and genetic level. So understanding how they arise, how do they present, will be helpful in formulating our conceptual basis of how to deal with very complicated tumors that I've listed here. The relative frequency of T-cell lymphoma subtypes, clearly there are 4 that are more common than the others. T-cell lymphoma NOS, even today, remain probably one of the most common subtypes, followed by immunoblastic T-cell lymphoma. The ALK-positive and ALK-negative lymphomas are next, and then the T and NK cell lymphomas. In countries like Peru, the relative frequencies of these are probably different, as we have seen Dr. Cox present earlier. And why is this important? It's important because our subclassification has prognostic information. The ALK-positive ALCLs, at least according to the International Lymphoma Project that was presented and published by investigators in Nebraska and others, show that ALK-positive ALCL patients do well, followed by ALK-negative ALCL patients, AITL, T-cell lymphoma, NOS, whereas those that are driven by viruses like the NK T-cell lymphomas that are associated with EBV, and ATLL that are associated with the HTLV virus have really, really bad prognosis. And this might not be a problem for hematopathologists in countries where you see a lot of T-cell malignancies, but in many other countries, because they're so rare and heterogeneous, they're diagnostically challenging. Okay? In addition, we're always pressed for accurate diagnoses, and the anxiety associated with these cases is worsened because they're thought to be clinically aggressive. Importantly, I think we've learned a lot about the normal counterpart of B-cell malignancies, the germinal center origin and the activated B-cell origin. In T-cell malignancies, I don't think we have as good of an understanding of the normal counterparts of many of the T-cells that give rise to the variety of T-cell malignancies. And until recently, our classification has been very complicated with low reproducibility because of the lack of robust biomarkers that can be used. Aside from the ALK-positive ALCLs, the utilization of routinely available biomarkers have been relatively missing until recently. In addition, T-cell subsets show a lot of plasticity, and so the immunologic and biomarkers that are available might not be as straightforward as we have used for the B-cell counterparts. And importantly, in contrast to the kappa and lambda, there are no reliable antibody-based markers to detect whether there's a clonal T-cell population. And so all of these contribute to making diagnoses of peripheral T-cell lymphomas quite a challenge. So this is a very simplistic overview of the T-cells and NK cells and our immune system. You can look at it from, there are two groups, the innate immune system. These are composed of NK cells and some T cells, the gamma delta T cells. They don't require prior exposure to antigen, and their response is quite evolutionarily primitive. Turns out many pediatric-focused T-cell malignancies arise from T cells in this part of the immune system. The adaptive immune system represents the majority of T cells. They're antigen-specific, immunologically memory T cells, and many of our T cell lymphomas that occur in the adult population occur from T cells that function in this part of the immune system. As I said before, T cell subsets and their functions show a lot of plasticity. There's a lot of crosstalk and flexibility in their lineage specification. So just focusing on CD4 positive T cells, there are numerous subsets. We recognize Th1 cells that may express certain transcription factors and secrete cytokines. Th1 expresses TBX21. Th2 cells express GATA3 transcription factor and secrete IL4 and IL5 and IL13. There are also Th17 T cells that express the RHOA gamma T transcription factor and express and secrete IL-17 and 22. How these contribute to our understanding of the putative counterparts of many of the T-cell lymphomas is currently not very well studied, although recent papers from Brian Wilcox's lab and John Chen has demonstrated that in peripheral T-cell lymphoma NOS, you could subclassify those into those that arise from the Th1, expressing the TBX21 transcription factor, and those that are of the Th2 subtype and express the GATA3 transcription factor. So, as kind of a broad conclusion of the introduction, clinically, pathologically, they're very heterogeneous. The genetic basis of many of these tumors were largely unknown until recently. So, as molecular diagnostic hematopathologists, we have counted on numerous technologies over the last 30 years to interrogate the genetic basis of many lymphomas. Again, just an overview of cytogenetics, PCR, the real classification system. And then I think recently the availability of targeted NGS panels for detecting structural alterations or mutations in many tumors from formal and fixed tissues have contributed to emerging information about the genetic basis of these T-cell lymphomas. So these are the topics that I'm going to be covering relatively briefly in this talk. So mutations that occur in follicular T-cell derivation are those that involve mutations in genes called RHOA, TET2, DNMT3A. So there have been a group of T-cell lymphomas that posed a diagnostic challenge, and it was understood that these might represent some gray zones of delineation. And these represent those that are represented by angioimmunoblastic T-cell lymphoma, T-cell lymphomas that have the TFH phenotype. There's some T-cell lymphomas, NOS, as well as a subset of ALK-negative ALCLs. And it had not been really clear, because of the lack of robust biomarkers, how these entities can be distinguished. And so some of the work that have been published in the last 10 years, this is work from Laurent Nodal, who showed using gene expression profiling studies over 10 years ago that if you look at angioimmunoblastic T-cell lymphomas and identify genes that are different between them and T-cell lymphoma NOS, that they were able to identify a signature that illuminated some understanding about the T follicular helper phenotype. This was followed by work from Javed Iqbal from Nebraska, showing that gene expression signatures can distinguish different subgroups of T-cell malignancies. And so the concept of genes that are relatively selectively expressed in T follicular helper cells was established. And so the TFH markers that are now recognized to be helpful are PD1, CD10, BCL6, CXCL13, ICOS, and several others I've listed here. These are all expressed in follicular T-cell derived T-cell lymphomas, namely being follicular T-cell lymphoma as well as angioimmunoblastic T-cell lymphoma. Using that approach, genetic studies have identified that these harbor mutations that seem to be enriched for RHOA, IDH2, DNMT3, and TET2. These are mutations, aside from the RHOA, that are also found in other tumors like gliomas and acute myeloid leukemias. The IDH2 mutations seem to be most specific for angioimmunoblastic T-cell lymphoma, and TET2 mutations notably can be found in other lymphomas like B-cell lymphomas. And so these are studies that show that some of these mutations may identify a cell of origin and help us distinguish these from T-cell lymphoma NOS. So RHOA mutations almost never are found in T-cell lymphoma NOS and should be found selectively in tumors that arise from the TFH subtype. What are RHOA mutations? RHOA is a protein that encodes for small GTPase. Expression in CD4 positive T cells induces a TFH cell specification, and studies from Adolfo Ferrando's lab demonstrated that when you express these in mice, they increase proliferation and lead to ICOS upregulation and MAPK signaling. And so it functions in collaboration with TET2 in developing AITL and using mouse studies. And importantly, the authors show that you can inhibit the ICOS PI3 kinase signaling pathway in RHOA mutated tumors by the use of selective inhibitors. So, as hematopathologists, I think we now have some better tools to distinguish T-cell lymphoma NOS from nodal peripheral T-cell lymphomas of TFH origin. And so the WHO recommends that to call something a TFH origin, you need to have the expression of 2, preferentially 3 of the markers, PD1, CD10, BCL6, or CXCL13, or anything that you can make work in your immunohistochemistry lab. Whereas the T-cell lymphoma NOS should not express more than one of the TFH markers. I think that will be helpful for the practice. All right, other genetic alterations that are found in T-cell lymphomas have been those that function in the T-cell receptor activation pathway. And many of these are found in a variety of T-cell lymphoma subtypes, AITL, T-cell lymphoma, NOS, mycosis fungoides, as well as Sézary syndrome. So these are not selectively enriched in certain types of T-cell malignancies. Mutations that function in chemokines, the cytokine receptors, GTPases, the NF-kappa B pathway, and cell cycle regulators, all activated and regulated by T-cell receptor activation, seem to be impacted by somatically acquired mutations in these protein components. This is a figure showing some of the high-frequency recurrent mutations that occur in components of the T-cell receptor signaling in TFH lymphomas. These are PLC gamma 1, CD28, PF3 kinase, and HARD11. So these might demonstrate, if they're present in a targeted NGS panel, that there is a pathogenetic alteration. Another group of genes that are recurrently mutated in many forms of T-cell lymphomas are genes that function in epigenetic modification. I'm listing a subset of them here. One is called SEPI2. The others that are frequently involved by mutations are TEP2 and IDH2. These are genes that are involved in chromatin remodeling. SEPI2 is a histone trimethylation associated protein. We see loss of function mutations in many forms of T-cell malignancies. This gene is involved in genome stability and homologous repair. And TEP2 and IDH2 are mutations that are also seen in CHIP. They seem to occur in myeloid tumors as well as in a variety of other cancers. And importantly, they acquire and accumulate during age. Another gene that is involved in chromatin remodeling or DNA methylation is called DNMT3A. This functions in conjunction with the TET hydroxylases to balance site-specific regulation of DNA methylation. It seems to be involved in the methylation and the transcriptional repression of many pluripotency genes that seem to be deregulated in many forms of lymphoma. They're frequently, again, mutated during the aging process and identified at low allele frequencies in CHIP. So it seems like if you put some of these data together, what has been shown to be relevant in TFH-derived T-cell lymphomas, which may be an effect in other T-cell malignancies, is that there are genes that regulate the epigenetic machinery, the TEP2, DNMT3A, and NPM1 mutations that are acquired early on during the hematopoietic and multilineage process. And then mutations that occur later on, such as the RHOA IDH2 and CD28, might be impacting the differentiation and proliferation pathways that are required for the full-blown pathogenesis of these. So another form of T-cell malignancies where the chromatin modifying genes and DNA methylation genes are highly prevalent is a form of cutaneous T-cell lymphoma that becomes leukemia called Sézary syndrome. This is an area that we also studied in our research lab. Aggressive T-cell malignancies, median survival of 1 to 2 years, and until recently, We have known that they have a lot of complex karyotypes by cytogenetic analysis with recurrent structural variants not being recognized. And so we thought that this could be a very fruitful area for investigation. So what we did was to carry out an integrated genomic study where we carried out whole genome sequencing of 6 index cases of Sézary syndrome patients. You can see here, these are circle plots that represent all of those genetic abnormalities that were identified from our whole genome sequencing. The lines between the different chromosomes represent rearrangements, gene structural rearrangements. While many had numerous gene rearrangements, there were none that were recurrent, not seen more than once in any of the 6 studies. We did identify rearrangements involving genes that were important in T-cell function, like FOXP1, EZH2, but none of them were recurrently identified. We also did whole exome sequencing of 74 Sézary syndrome patients and identified recurrent areas of aneuploidy involving a number of chromosomal regions like 1p36, 3p21, some of which have been shown and to be identified and present in these tumors. This is a figure demonstrating that p53 was recurrently targeted by both aneuploidy as well as somatic mutations in a large number of Sézary syndrome genomes. So it met the two-step hypothesis that it was impacted by loss of heterozygosity as well as the acquisition of a second mutation that leads to complete aberration of this tumor suppressor function. Another gene that we identified, recurrent loss of function, as well as LOH, was in the gene encoding ARID1A. This is another gene that's involved in epigenetic remodeling, found in 40% of the Sézary syndrome genomes. This is a figure demonstrating the highly frequently impacted genes that are involved in DNA modification, the ARID proteins, the PET 1, 2, 3 genes, GNMT1, 3, 3A, 3B, 3L, histone modifiers, the MLL gene family set proteins. They were recurrently mutated in a large number of Sézary syndrome patients. So this was a study that was published at the same time as 5 other papers that demonstrated for the first time that this very aggressive form of T-cell malignancy harbored alterations in epigenetic modifiers as well as some components of this JAK STAT pathway. So the JAK STAT pathway is a very important signaling pathway in T-cell function. And notably, many components of that same signaling pathway seem to be altered by rearrangements as well as somatic mutations in many forms of T-cell malignancies. It seems that if you look at a certain form of T-cell malignancy or subtype, there seems to be disease selectivity for JAK1 or JAK3, STAT3 or STAT5B. They typically don't occur in the same tumor. This is an example of a group of diseases that we selected for study in our research lab several years ago. This is T-cell lymphocytic leukemia. This is, again, another very aggressive form of mature T-cell leukemia, typically involving elderly patients. They present with elevated white counts, as well as lymphadenopathy and hepatosplenic. And many of them have a very dismal prognosis with median survival of 1 year. Cytogenetically, we had known for many decades that these patients have characteristic rearrangements involving the MCTP or T-cell locus involved by either inversion 14 or the X14 rearrangements. They also harbor trisomy 8 and isochromosome AQ, and ATM alterations have been identified. But recurrent somatically acquired mutations in these tumors have not clean. So we carried out a large integrated genomic analysis of a large number of patients with T-cell PLL, and this is again a surplus plot demonstrating that we were able to see numerous areas of chromosomal losses and chromosomal gains in the genome of these patients. This is a figure demonstrating that ATM locus, which is found in the 11q14 to 11q25, was recurrently deleted in many patients with T-cell PLL. We also saw evidence of isochromosome 8 in many of these genomes. When we looked at the whole exome data, we also identified somatic mutations in the ATM locus. This is a figure showing that the mutations were found in the CD4 positive enriched tumor cells, but not in the normal T cells, demonstrating and confirming that these were somatically acquired mutations in certain domains of this protein. Importantly, we identified mutations in the IL2 receptor gamma gene, the JAK1, JAK3, and STAT5B genes that seem to be highly recurrent. So mutations in JAK1 and JAK3 were focused on the autoinhibitor pseudokinase domain and the kinase domain, whereas the mutation in the STAT5B transcription factor were focused on the SH2 domain that mediates the STAT5B interactions. So we demonstrated using Western blot analysis that if you express these mutations that we identified in the patient-derived material in cell lines, that they induce STAT5 transcriptional activity, demonstrating that these mutations have an impact on the transcriptional signature. So if we express the mutations in lymphoid cell lines, show that there is enhanced proliferation, colony formation, and when we use a selective STAT5B inhibitor called pimoside, we were able to show that the tumor cells that harbor the mutations in JAK1 or STAT5B show decreased cell proliferation and viability, demonstrating that these mutations have pathogenic relevance. So these studies demonstrated that JAK STAT mutations were found in over 75% of T-cell PLL. Importantly, this is the first description of high prevalence mutations in these form of aggressive tumors. Mouse modeling studies that have been published over 10 years ago had demonstrated that if mice have the TCL1 rearrangement, it was not sufficient to form aggressive tumors. And so we believe that JAK STAT mutations contribute to the aggressive behavior that many of these patients are impacted by. And so the importance of our work demonstrates that potentially small molecule inhibitors to either the JAK protein or the STAT5 proteins might have a therapeutic strategy for these patients. Another form of T-cell malignancy that occurs in the GI tract also have shown to have recurrent mutations involving the JAK STAT pathway. So these are two different types of intestinal T-cell lymphomas. In the past, they used to be called AITL1 and AITL2. They're now called enteropathy-associated T-cell lymphoma and monomorphic epitheliotropic intestinal T-cell lymphoma. The first type occurs usually in people who have history of celiac disease of Northern European descent, usually occur in T-cells that have the alpha-beta phenotype. And these tumors harbor mutations in STAT5B, JAK3, and another protein called GNA12. Whereas the monomorphic form of the intestinal T-cell lymphomas are typically gamma delta T-cells. They're epitheliotropic. They tend to occur in the Asian Hispanic population, And while the mutations that are seen in this form of tumor are, there is some sharing of overlap of the mutation, like STAT5B and the JAK3, they preferentially have mutations in the SETP2 protein or gene that is almost not seen in the AITL type 1. So the presence of SETP2 might be able to provide support that this is a monomorphic epithelial-trophic T-cell lymphoma versus AITL. The contribution of that gene mutation to pathogenesis is obviously going to be an ongoing research question. Another form of T-cell lymphoma that occurs in the GI tract, this is a relatively new entity. It's a new provisional entity that we all should be aware of. Importantly, these are considered to be indolent, and treatment only is going to require surgical excision. They typically look like Crohn's inflammation. They represent clonal expansion of cytotoxic CD8 positive T cells that typically involve the lamina propria with alpha beta T cells. They have low proliferative index and clinically they are indolent. Recent studies from Andy Feldman's group demonstrated in 4 of their patients, they identified a gene fusion involving STAT3 and JAK2. So this is the rearrangement that is found, and it's thought to potentially contribute to activation of the JAK STAT pathway. You can see that the phospho-STAT5 protein is shown to be localized to the nucleus in the tumors of these patients. Hepatosplenic T-cell lymphoma is again another rare form of T-cell malignancies. They occur in young adults, typically present with hepatosplenomegaly and these symptoms, commonly associated with immune suppression following organ transplant or patients who are being treated for Crohn's disease or other inflammatory bowel disease. They're aggressive and typically they involve bone marrow, spleen, and the liver, showing a very sinusoidal pattern of infiltration. They're typically gamma delta T cells, TI1 positive, and granzyme B is typically negative. Associated with the presence of isochromosome 17, which has been diagnostically useful if you had cytogenetic information. And recent studies again have shown that they have high frequency mutations in SETP2, STAT5B, and STAT3 in some of these. Another area that has received some attention and expanded our understanding of the disease entities is ALK positive and ALK negative ALCL. And so this area demonstrates that multiple mechanisms of STAT3 and 5 activation lead to anaplastic large cell lymphoma. And so we have known over 25 years that the ALK positive lymphomas harbor the rearrangements involving the ALK tyrosine kinase. This was the work done by Steve Morris and Tom Look over 25 years ago. What we don't know, or what we haven't really known very much about, is the ALK-negative anaplastic large cell lymphoma. So just as a brief summary, NPM-ALK positive ALCL, it has been a very useful biologic tumor model for studying the ALK tyrosine kinase. This is a rearrangement that occurs as a result of fusion of the N-terminal portion of nucleoplasmin and chromosome 5 with the tyrosine kinase portion of anaplastic lymphomal kinase on chromosome 2. And the fusion transcript encodes a fusion tyrosine kinase, resulting in ectopic aberrant expression and activation of anaplastic lymphoma kinase in T cells that typically don't express the anaplastic lymphoma kinase. And so we understood that autophosphorylation that results from the dimerization of these proteins lead to multiple downstream signaling pathways that contribute to enhanced proliferation and invasive properties of anaplastic lymphoma kinase. The WASP story is one where Carlos Morgan-Zamayoa has contributed to what was a training that he continues to pursue his research. So ALK is importantly rearranged and mutated in a variety of human cancers. It's involved in ALK-positive ALCL, inflammatory myeloblastic tumors, another rare pediatric soft tissue tumor. We're also involved in non-small cell lung cancers, diffuse large B-cell lymphomas, and mutations occur in neuroblastoma, so sporadic and inherited. And ALK is known to be now a therapeutic target, and small molecule inhibitors like crizotinib and other third, even fourth generation ALK inhibitors are being currently evaluated through clinical trials through the COG. So the genetic basis of ALK-negative ALCL has largely been unknown until recently, and I'm going to skip over these. We identified the NPM-TYK2 rearrangement in a subset of ALK-negative ALCLs. Andy Feldman's laboratory also demonstrated that rearrangements involving a gene called DUS22 are found in about 10% of ALK-negative ALCLs that occur in lymph nodes. They also occur in cutaneous anaplastic large cell lymphoma that are ALK-negative. And it's thought that downregulation of this dual specificity phosphatase inhibits T-cell receptor signaling and enhances growth. Interestingly, in this form of ALK-negative ALCL, there's absence of STAT3 activation. And this is thought to lead to a tumor that alters the DNA methylation pattern, leading to enhanced immunogenicity, high CD58 expression, and HLA class 2 expression, potentially contributing to a different clinical outcome for these patients. EP63 rearrangements are also seen in ALK-negative ALCLs, very rare, and immunochemical studies can be used to demonstrate the rearrangements, but they're not specific for the genetic abnormality. So we can now recognize that there are at least 4, maybe 6 different types of rearrangement in ALK-negative ALCL. Importantly, this study that was published a couple of years ago demonstrates that there are prognostically important information in the detection of these rearrangements in ALK-negative ALCLs. Thus, 22 rearranged cases have best survival overall, whereas TP63 rearranged cases have really dismal outcome, whereas the triple negative cases do intermediate. Another type of anaplastic large cell lymphoma that's ALK-negative is the breast implant-associated ALCL. This is a provisional entity in the WHO associated with seroma surrounding breast implants. They're characterized by strong CD30 expression, absence of ALK protein expression. Patients typically do very well with removal of the capsule, but if there is invasion of the breast tissue or formation of a tumor mass, the patients do have a higher incidence of developing systemic disease. Notably, recent studies have shown that potentially 30% of the cases that have been investigated have mutations in the STAT3 gene, again, demonstrating that these, the STAT3 pathway is implicated in the formation of anaplastic large cell lymphoma. So these are kind of the different prognostic and therapeutic importance of subclassifying ALK-negative ALCLs. We need to recognize that there are a variety of different gene rearrangements as well as gene mutations involving STAT3 in this provisional entity. And I anticipate that over time, very soon, that these may become distinct subtypes within the WHO. Now, again, I mentioned that T-cell lymphoma, NOS, again, still represents a wastebasket category, but couple of studies have shown that if you use a nanostring-based gene expression profiling approach, you can distinguish two large groups within the NOS category. One that shows a Th1 phenotype, the other one a Th2 phenotype, and the Th2 phenotype tends to behave more aggressively. So I think we're going to hear more about this potential subclassification scheme from the LLMPP. So it seems like gene fusions occur in many forms of T-cell malignancies, and in 4 or 5 years, many of the NOS cases are going to be genetically characterized as having a variety of different kinds of genetic alterations, including mutations. We have learned a lot about T-cell lymphoma development and potential postulated normal counterparts, and the mutational signatures that seem to be enriched in some of those, whereas others are shared between many of the different subtypes. We are approaching the era of a genomic classification of T-cell malignancies. Our laboratory that's led by Dr. Johnson, we went live with a lymphoma NGS targeted panel, which may help us in distinguishing some of the entities within this kind of complex group of diseases. So why is this important? It's important not only for diagnostic accuracy, we will be able to demonstrate and potentially identify patients that are eligible for novel clinical trials to evaluate the relevance of these inhibitors that target many of these altered pathways. And chemicals and targeted therapies for many of these altered gene products are being evaluated. So what's going to be ahead of us? Emerging technical applications, again, molecular diagnostic signatures of PTCL subgroups based on gene expression, because we can't do this by eye or even by immunohistochemistry. Targeted NGS panels for subclassification and identification of targeted therapies are going to become more and more relevant. High throughput sequencing of T-cell receptor, which is really very highly sensitive for detecting clones and identifying clones, might be useful for establishing diagnoses integrated with the rest of our pathologic evaluation and for disease monitoring. Circulating tumor DNA for early disease detection and disease monitoring are going to be important. And so work from some of the B-cell lymphoma patients, they have been using circulating free tumor DNA for MRD for many patients with diffuse large B-cell lymphomas. They have found that retrospective and prospective studies show accurate genotyping to detect mutations. And importantly, this is a non-invasive tool to potentially track clones of tumors that might be resistant to the treatments that we have exposed. So really in the future, we're going to be accountable for integration of high-dimensional data for our pathology practice with H&E, immunohistochemistry, 10-color flow, cytogenetics, FISH, RNA transcriptome or gene expression profiling, targeted sequencing, imaging, metabolism. We're going to be able to integrate this information to make recommendations for treatment and more effective disease monitoring so that we can be very effective in delivering high-quality patient care. So just to summarize my talk, T-cell malignancies are highly heterogeneous, ranging from very indolent processes to really highly aggressive diseases. Judicious application of molecular testing is important for establishing a diagnosis. We never make a diagnosis based just on flow or based on molecular. And so even if we have nanostring platform or NGS panel, our diagnostic approach should not depend on one platform. Molecular diagnostic signatures of T-cell lymphoma subgroups based on gene expression profiling may be helpful in the PTCL NOS cases. The genetic basis of many of these tumors continue to be elucidated and clarified, and the targeted therapies will be available, requiring additional testing for disease monitoring, because ultimately all of the patients who receive targeted therapy develop resistance to those treatments. And so to be able to monitor patients more closely, we're going to be utilizing more of the non-invasive tools such as tumor DNA, flow cytometry, or disease monitoring. So I want to acknowledge all of our collaborators. We've worked with a lot of talented hematopathologists from Peru. Roberto Miranda is a close friend of ours, as well as Carlos, and all of our collaborators, and funding support for our work. And I'll finish there and take any questions.